All right, so last section for this week, we're going to take a look at counting. And counting is kind of the introduction to what we're going to finish up with, which is probability. So counting basically looks at how many ways something can happen. For example, if I said to you, I want you to think of 3 letters, like A, B, C, and I asked how many different passwords could you make with those letters? Saying you don't repeat, you know, ABC, BCA, things like that. Now, if I said to you, what are the chances that somebody picks the password BCA? Well, then we'd have to know how many total ways they could make a password, and that would be our denominator. And then how many ways could they pick the password we want? Just one way. So it would be 1 out of however many total there were. Okay, so to figure out that total, we have to learn how to count. The probability can get a little bit complicated, okay, depending on what you're finding the probability of. For example, if I said flipping a coin, what is the probability of getting heads? That's simple. It's just 1 out of 2, 50%. But if we started to look at a problem like, what's the probability if you're exposed to a certain disease that you contracted? We can statistically maybe calculate based off of how quickly something spreads and how dangerous the infection is and things like that. But still, it's not something we could predict exact, right? Because there's too many other variables that affect it. So you might see that with like the flu shot. Okay, each year they statistically try to predict what they think is going to be the most dangerous strains of the flu, the most common ones, and they try to create a vaccine that protects you against those strains. Sometimes they don't do a good job of predicting and the vaccine isn't as effective. Sometimes they do a really good job, okay, and it's very effective. But again, it's all probability. It's all just taking an educated guess based on theoretically what you think is going to happen. All right, so that's the kind of stuff we're going to look at more next week. All right, so counting basically asks the question, how many ways can something occur? Okay, how many license plates could you create? How many passwords could you create? How many ways can, out of a group of 20, can you have a top 3 finish? Okay, what are the different amount of ways that can happen? Right, so that's what we're going to be focusing on, okay, counting. For a couple problems, we'll try drawing it out and actually making lists, but eventually we'll see why making lists might not be the best way to do a counting problem. Okay, let's start with this one. Okay, using the letters A, B, C, D, I want to know how many different 3-letter codes I can form. Okay, so I have 4 letters to pick from. You are allowed to pick 3 at a time to create passwords. And let's assume that no letter can be repeated. Okay, so no repeated letters. If I didn't add that last part, that's a vague question. You need more detail, whether or not you can repeat letters. All right, so we want to try to list things out in a systematic way. So what do you think would be a good way to do this systematically?
Start with A first.
Yeah, start with the alphabetical, okay? We'll start with ABC, and let's list all the different passwords we could make from that. We'll do it in alphabetical order. So we have ABC. So for now, remember, we're just going to pick 3 letters at a time. So let's do everything we can with the 3 letters ABC. And then we'll move on, and we'll do everything we can with other letters.
ACB.
We could do ACB. Yep. What else?
BCA.
BCA. All right.
BACB.
BAC.
CAD.
CAB. Okay. And CBA. Those are all the different combinations of passwords you can make with the letters A, B, and C. So what letter did we leave out?
D.
We left out D. Okay, so sometimes what I like to do in my head is think of what did I leave out, and then that tells me maybe a pattern to try to list everything out systematically. So we left D out. Let's try leaving C out. Okay, and then we'll try leaving B out and A out, and we'll make all the combinations we can. So now I'm going to use the letters, what did we just do? Yeah, let's leave We did that one. Let's leave C out. So A, B, and D. Okay, what would be the passwords I could make with A, B, D?
ABD,
Yep, A, B, D.
ADB,
A, D, B.
BAD,
B, A, D. Yep.
And you just replace the C with the D and
Yeah, we're really just replacing all the C's with D's in this case. Yeah. Next one.
DAB,
D, A, B. Yep.
DBA,
And D, B, A. Okay, so we got those. Now we have, let's leave B out, so we could do A, C, D. All right, passwords with A, C, D. Yep, we have ADC, CAD, CDA, DAC, and DCA. Okay, and we have one more grouping of 6 that's leaving A out. So BCD. BDC, CBD, CDB, DBC, yep, and CB. Sounds like we're saying the same thing over and over. So, how many different passwords can we create? 24. Hey, so making a list here, not too bad, but again, if I even just said you can pick from, I don't know, let's up it to 7 letters, and you can pick 4 at a time. Now it's going to go up quite a bit. Okay?
So how do we figure that out?
So now, yeah, we're going to look at a way we can just do that without listing them. I'll show you in a little bit. Okay, another way you can list out small possibilities is you can make a decision tree, okay, or a tree diagram. Okay, so for this one, it says that an animal is going to perform 2 tasks. For each task that it performs, it's going to get 1 reward. Once it gets that reward, it can't get it again. So think of it as like you have 3 different pieces of food, okay, 3 different treats. Once you feed that to the dog, when they do the second trick, they can't get that treat again because they already ate it. Okay, I want to know how many different sequences of rewards could the animal get. All right, so we're going to start with a tree. So I'm going to scroll back up in a second. Okay. When the animal performs the first trick, how many different choices do you have for the rewards? Yeah, the animal hasn't eaten any of them yet. You still have all 3 rewards in your hand. You can give the animal any one of the 3. And to make it simple, what could we call those rewards?
R1, R2, R3.
Yep, you could call it reward 1, reward 2, and reward 3. You could have used ABC, that's fine. Okay, and that's after trick 1. Okay, now the animal is going to perform trick 2. Okay, and once it performs trick 2, if it got reward 1 the first time, what's left for it to get the second time? Yep, it could get either reward 2 or reward 3. What if the animal got reward 2? It could get reward 1 or reward 3. And now, what if it, let me just move this down, what if it got reward 3? Rewards 2 and 1 are still left. So how many different reward paths are there? 6. Yep. Assuming you can't give the same reward twice. What would happen here if I said, you know what, you have as many of each reward as you want, so you can repeat? How many reward paths would there be if you could repeat? It would be 9, because then after getting reward 1, you could get 1, 2, or 3 again. After reward 2, you could get 1, 2, 3. after reward 3, 1, 2, 3. So there'd be 9 reward paths. Okay, any question on that tree? Okay, another problem I think of as a tree problem is picking out, say, food at a buffet. Let's say you had a choice of, I don't know, 3 entrees, 4 drinks, and 2 desserts. Okay, I can kind of think of that as a tree to figure out how many different meals can I make, where a meal consists of an entree, a drink, and a dessert. Okay, what's that?
Can we name the desserts?
Well, we're not going to go through it, but yes, if you were actually doing it, you could name them.
He just gave you the.
Okay, and with that kind of problem, it's a little different because what I would do is assume that, let's say I pick turkey sandwich. Okay, if I pick a turkey sandwich, that shouldn't have any effect on the drink that I pick. I could still pick soda, I could pick water, I could pick lemonade.
What if you prefer a turkey sandwich with like a root beer?
Well, you could, but you can still get whatever you want. Now, if let's say there's rules in place that are something like, well, if you pick turkey sandwich, then you're limited with the drinks you can pick. Then that messes up my tree a little bit. Okay, I'd have to be a little bit more careful how I draw it.
Well, yeah, if
Okay.
you put constraints on it.
Yeah, if you put constraints in it, then it ruins kind of the symmetry of the tree, depending.
But it also narrows down the choices.
But yep, can narrow down some choices. All right, another thing I would think of in this kind of thing is like if you were buying an outfit. Let's say you had a choice of 5 shirts, 4 ties, and 3 pairs of pants. You could figure out how many combinations of outfits can I make, and you could do a tree to do that. Okay? But how come a tree diagram isn't always practical? Yeah?
There's a lot of different options. It's be really lengthy.
Yeah, so it can start to become time consuming. Okay, so the tree gets big, takes a lot of time to draw it. So we want a better way to count, right, other than making lists for a tree. So that's where the fundamental counting principle comes in. Okay, and this principle is contingent on something I mentioned earlier. But as long as it meets the criteria, which I'll tell you in a second, if you have A ways of making your first choice, B ways of making your second choice, C ways of making your third choice, you can have as many choices as you want. Okay, but I'm just doing it for 3. The total number of possibilities is the number of choices for the first one times the second one times the third one. So if I was making outfits again and I had a choice of 5, just make it simple, 5 pairs of pants, 4 shirts, 3 ties, and I wanted to know how many different combinations, 5 times 4 times 3.
A lot of combinations. You'd be in that dressing room a while.
Yeah. Okay, and again, that can be extended to as many choices as you need to make. So now you could add in, belt with that. Maybe you got 2 different belts, shoes, as many choices as you need. You can keep extending it as long as the choices are independent from each other. Okay, which obviously for picking out an outfit, certain things would influence other things. But if all your choices are independent, okay, this method works. So in other words, whatever you pick for the first choice doesn't limit your options for the second choice. And whatever you pick for the second choice, that doesn't limit your options for the third choice or any other choice you have to make. Okay, so any question on the fundamental counting principle? All right, so let's use that idea with license plates. Okay, so we're going to make license plates, and the license plates are going to consist of 2 letters and 3 digits, no repeating letters or numbers. So once you use a letter, that letter is used, it can't be used again. I want to know how many different license plates I can make. So generally what I do is kind of set up a diagram. where that represents my license plate. And I'm picking 2 letters followed by 3 digits.
Is it followed like really arbitrary?
Doesn't really matter, though.
What's that?
Like does it have to be like letter letter then number number number, or can it be like letter number number letter number?
It turns out with what we're going to do, the number of possibilities would really be the same.
Okay.
But what you're getting at would give us, how can I say it? Numerically, if I calculate the number of possibilities with this and say the way you said it, switching every other, we would each have the same number of possibilities. We would have different possibilities, but my number of possibilities and your number would be the same. Make sense? So like maybe I have 100,000 ways to do it, you have 100,000 ways to do it, but your individual orderings would be different than my individual orderings.
Okay.
But we'd each have the same number of orderings. They just wouldn't be the same orderings. You would have a different pattern to yours. I'm going to have letter, letter, number, 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 and you have number, letter, whatever you said, number. All right. So first thing we're going to look at is how many ways we could choose the first letter. Okay. How many choices do we have?
26.
Yep. Very first letter, we have 26 choices. And regardless of what letter you choose, how many do you have for the second letter?
25.
You have 25. Okay, now how about for my digits? How many choices for the first digit? 10.
No.
I would put a 0 in there, too.
Yeah, we can include 0 is considered a digit. I'll talk about restrictions in a second, which are important, but 10. How about the second digit? And the last digit? 8. So if we multiply 26 times 25 times 10 times 9 times 8, it's 468,000 different license plates.
Man, we're not run out of phone numbers, huh?
What's that?
That means we can, like, make a crap ton of phone numbers.
Oh, you can make a lot of phone numbers, yep.
Like, now we're gonna-
But with phone numbers, we have to be careful, okay?
What if we run out?
Any questions on how we got 468 first? Okay, let me show you why with phone numbers we have to be careful. Okay, let's think of extensions in this building. Every extension is a 4-digit extension. And how many choices do you have for each digit?
9,
Well, in this building, you can have an extension like 2429. You can have a digit repeat. So yeah, 10 times 10 times 10 times 10. So 10 to the 4th power. So in theory, there's 10,000 extensions you could have. But it's really not that high.
Isn't it like based on the building you're in?
How come? Anybody know? You'd have to know a little about the phone to know why there's certain restrictions. The first digit cannot be anything you want. I'll give you a hint.
Isn't that based on like the building you're in?
Based on, yeah, the way the extensions are distributed, yeah. But right now, we're just looking at how many are in the total pool of extensions. Anybody have any thoughts about the first digit? Think about telephone numbers.
That's not what
You have to start with an area.
Okay, what are area codes not allowed to start with? 0. You can't have an area code start with 0 because if you press 0, that goes right to the operator, or here it goes to the main office. So really, you don't have 10 choices for the first one. You can't use 0. And you also can't use the number 9 in this building because 9 is what you press for an outside line. So if I press 9, it immediately goes to an outside line number, and I can't dial in the building. As far as other extensions, everything else is fine. Okay? So in theory, you would have 8 times 10 times 10 times 10 extensions. Still a lot of extensions. Okay, but that's what gets hard when you start getting into counting. You have to think of all the different things that you might not be allowed to do. Okay? Maybe we would also want to say we don't want any extensions where all 4 digits are the same. So you can't have the extension 4444 for whatever reason. So then we'd have to take out 10 more extensions. Actually, we already took out the one that would have started with 0 and 9. We'd have to take out 8 more. All the ones that start with 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s. Okay. So sometimes that can get a little tricky. Any questions on that? All right, let's look at this one. Okay, there's 8 runners in a race. I want to know how many different ways the runners can finish. Okay, so here's our 8 runners. Does anybody have any thoughts how you would figure out the number of ways the runners can finish? It's actually something we've done before. At least there's a way to write the answer using some symbols we've done before. Yep, it has to do with a factorial. Mm-hmm.
Like if the 8 runners would be like 8 factorial.
Yes, this would be 8 factorial. Because the first, if you want to pick how many ways can first place finish, 8. And I think this is one, it should make sense once somebody finishes, they're not finishing again. They finished, they're done. Now there's 7 runners left, and then 6 runners, and then 5, 4, 3, 2. And by the time 7 runners finish, you're basically done. The 8th person is just going to finish in 8th place. Okay, so it's times 1. Right, so 8 factorial would be pretty big. I don't think I have a factorial button on here. Let's see if I do it like this. Nope. So it's still pretty big. I type that correct. So it's 40,320 different ways. So now if I said to you, what are the chances that you pick the 8 runners in exactly the order they're going to finish, you would have a 1 in roughly 40,000 chance of doing that.
Sounds like a lot. Well, it depends if you use stats about that too.
You could that's why it gets a little bit more tricky, because then you could factor in statistics. Maybe you know certain runners usually finish higher and things like that. So you might have a little bit better chance. But if you were to just randomly pick 8 people, those would be your odds. So that's more like a lottery. You just randomly pick 8 numbers or whatever. Okay, and if we have time, we could, not today, but maybe tomorrow, we could look at like a lottery game and see what are the odds of winning. Because any lottery game, they have to publish the odds. You can go on the website, or if it's a scratch ticket, it usually says the odds, and we could do the math out and see are the odds really correct. And they should be. All right, so in both of those examples, we use the fundamental counting principle for the license plates and the runners. And when we're ordering letters in a license plate, ordering runners in a race, both of those are examples of permutations. Okay, so a permutation, in our last example, we did a permutation of 8 elements. Okay, and basically a permutation is just a specific order. That's all it is. A permutation is a specific ordering of your elements. Letters, numbers, people, okay, whatever it is. The key with permutations is that it has to be in a specific order. Okay, that's important. With a permutation, the order matters. Okay, so for example, if I said to you, I was programming, one of those cars that has the buttons on the handle, so you can type in digits, and I was programming that to open my trunk, and I picked a code. Would the order of the digits matter? Yeah. Even if I told you the digits to open my trunk are 3914, unless you try every combination, you don't know which combination it is. The order is important. Okay, so if you're not sure if order is important, ask yourself, would it make a difference if I change the order in this problem? If it makes a difference, then yes, order is important. Okay. So we saw this in the running problem, but if you have n elements and you want to know how many ways can you order all of them, it's n factorial.
You mean N?
Or yeah, you can get excited about it, n. But that's only if you have n things and you're going to order all of them. Maybe in here, let's say we're going to have a race and I only want to know the top 3. How many different ways can I predict the top 3 runners out of 13? Okay. Well, that's a little different. Okay, I have a better chance at picking the top 3 because I'm only picking the top 3 slots. You're not making me pick all the slots. Okay, so I'd have a better chance of doing that. Okay, so sometimes we only want to order a subset of our elements. Okay, in other words, we don't want to order all of them. Okay, in our next example, that's what we're going to do. We're going to look at ordering a subset of all of them. Okay, so here's an example where we're creating an order. We have 15 people we're going to pick from. And out of those 15 people, I want to pick 3 to be president, vice president, and secretary. So we have president, vice president, secretary. Now, if you think of it this way, I think it helps you to figure out whether the order matters or not. When I pick the 3 names to put on these lines, does it make a difference? Let's say I use the names ABC. If I write ABC or CBA, is that different? So if A is president, B is vice president, and C is secretary, is that different if I make C president, A vice president, and B secretary? That's different, yes. Okay, so this is a problem where the order does matter because you are assigning a specific position to each person. Okay, anytime you're assigning a position, a name, a title to someone out of a group, titles make order important. So out of the 15 people, yeah, Corey?
So something like this, is it going to be like just like at random, like you just randomly selecting people?
Yeah, we're just randomly, we have 15 people to pick, and we're going to pick 3 people and put them in specific roles. All right, so how many ways could I pick the president? 15. And how about the vice president? 14. Okay, we're assuming that no person can hold 2 positions. It doesn't say that, but if you ever have a question about an assumption, you can always ask me. So 14, and how about the secretary? 13. So 15 times 14 times 13. There's 2,730 ways I can form a president, a vice president, and a secretary. 2730. Any questions on that? Okay, another way you could think about it, this would be a little harder, but you could say to yourself, all right, how many ways could I just choose 3 people? Okay, let's forget about giving them roles. Okay, figure out how many ways can you pick 3 people, and then you could figure out, all right, once I decide I'm going to pick the 3 people, how many ways can I arrange those 3 people in the positions president, vice president, and secretary? We don't know how to do that yet. You know how to do the second part, but how many ways can you just pick 3 people out of 15 and not give them titles? Just form a group? We're going to look at that next. Nope, as in right now. Yeah. Okay, so what we just did, that was called an R permutation. Specifically, we permuted 3 elements out of 15. Okay, we did an ordering of 3 elements out of a total set of 15. And the notation for that is NPR, where N is how many total elements you have, and R is out of that total, how many are you going to create an ordering for. Okay, so the notation for the last problem would be 15 P3. Okay, hopefully it's obvious that R can't be bigger than N. Okay? Because N is how many total things you have. You can't order more things than you have. And if you tried to, well, strange things would happen. Because we have a formula that allows us to calculate NPR. It's n factorial over n minus r factorial. If you made r bigger than n, you'd end up with a negative factorial in the bottom. That doesn't, you can't do negative factorials. So let's take a look at example 5 again, just trying it with the notation I just showed you. 15p3. 15p3. So if I wanted to calculate that out, what would go on top? 15 factorial over 15 minus 3 factorial, which is 12 factorial. Now, you don't want to type this in, because remember, the numbers can get pretty big. You can cancel most of this out. Right. The top is 15 times 14 times 13 times 12 all the way down. Well, everything from here down is going to cancel out. Okay, 12 times 11 times 10 times 9.
So would that be over 1?
Yeah, it's just a 1 in the bottom. Okay, so all we're left with is 15 times 14 times 13. That's exactly what we got looking at it this way. 2,730. Any questions on that NPR notation? Yep.
So you just like start with your number and then just like do factorial down as many like slots as you have as you want?
Yeah, because if I was going to write this out all the way down to 2, all the way down to 1, and then in the bottom you've got 12 times 11 times 10, all the way down to times 2 times 1. Well, everything from 12 to 1 is going to cancel out. And you're left with 15, 14, 13. Yep. So any questions on permutation of n elements taken r at a time? All right. So let's try this one. 5-letter codes. I want to know how many 5-letter codes using the entire alphabet. This time we're not going to list them. No letters can be repeated. So what would be my notation? 26p5. So as a fraction, it would be what on top? 26 factorial over 21 factorial. So yep, 26 times 25 times 24, 23, 22. Okay, and I think if we do that out, it comes out to around 7.8 million.
Yeah, so no wonder why the government's having such a hard time cracking into the
Okay.
iPhone.
So 7,893,600, which might seem like a lot, but if you have a computer that could randomly guess 10 million passwords a second, this password would be cracked in under a second. Now that was assuming that nothing repeated. What if things repeated?
Well, maybe 26 times 26 times.
It would be 26 times 26 times 26 times, so it would be 26 to the 5th power. So you get a few more passwords, not that many more. You get about 3 million more, but still if the computer could guess 10 million passwords a second, it would be guessed in just over a second.
How many iPhone combinations would there be?
I'd have to know if there's a limit to the length of the password. If you had any password,
Say this 6.
6?
Yeah, 6.
So you could probably have uppercase, lowercase, and digit.
No, just digits.
Oh, just digits?
0 to 9.
So if you had 6 and you could
0 to
do,
9 and it can be repeated.
if it can be repeated, it would just be 10 to the 6th power. Well, 10 cubed is 1,000, 10 to the fourth is 10,000, fifth is 100,000, sixth is a million.
So you have a million, then two is on top of it after like the first six, it just prolongs it. So it takes a while for it to be cracked.
Yep, every time you add another, if it's just digits, you're adding another factor of 10, times 10, times 10, times 10.
So if it was 7 digits, does that mean it'd be
10 to the
like
seventh.
10 million?
10, whatever 10 to the seventh is, yeah. Yep.
That increases a lot.
Yeah, plus when you think though too is after like every the first six, it locks it out.
And if you're using, if you're not just restricting yourself to numbers, but you're using letters, numbers, and symbols, you figure there's probably 70 choices per character. 26 lowercase, 26 uppercase, 10 digits, and I'm just saying 10 or so symbols.
Look into it that much. It's a lot.
So yeah, there's a lot. There's a lot of different choices. Yep. All right, so last thing we're going to look at is a combination. Okay, the big difference with a combination is the order does not matter. And most of the time we see this kind of problem when you're talking about a committee of people. If I said I'm going to form a committee of 3 people out of the 13 in this room, a committee of Corey, Heaven, and DJ, or a committee of DJ, Heaven, and Corey, it's the same committee. I'm not giving titles to anybody. They're the same 3 people on the committee. Another example would be a handshake. If I said, out of 13 people, how many ways can I have people shake hands? Okay, I'd have to be careful I don't count things twice, right? Because DJ shaking hands with Corey is the same as Corey shaking hands with DJ. It's the same handshake, right?
Depends who reaches out for it though.
Yeah, we don't care who reaches out first. All right, so with something like that, that's a combination. Okay, the order, whether I call it Corey DJ, DJ Corey, same handshake, doesn't matter. Okay? So any questions on that? So things like passwords, order matters. If I was ranking the top 5 cars of 2016, order matters. If I was creating a code for an alarm system, password for a computer, order matters. Committees, order does not matter. Handshake, order does not matter. Okay? If I said to you, I want you to take 3 coins, throw them in the air, and I want to get 2 heads and a tail, order doesn't matter. You could get heads, and a tail on coins 1 and 2, or maybe you get heads, tails, heads. You get heads on coin 1 and 3. Okay? The order you get the heads in doesn't matter. Okay? And you could view this as either throwing 3 coins in the air at the same time or flipping 1 coin 3 times. It's exactly the same experiment. So any question about when order matters or when order doesn't? All right, so let's look at this one. How many committees can I make? 3-person committees if I'm allowed to choose from 4 people. Right, and let's list them all out. What would be an easy way to describe my 4 people?
A, B, C, D.
Yeah, just use something simple, A, B, C, D. What's that? Nope, this is going to be different. Yep, it's going to be different than the first one. Because it's a committee where the order does not matter. It's just a group.
It's going to be 4.
So somebody give me 1 committee I could make.
A, B, C.
A, B, C.
A, C, D.
A, C, what?
D.
D. Okay, so we left out D, we left out B,
A, B, D.
A, B, D. Now we just left out C
B, C, D.
and B, C, D, 8, or 792. Now, if I then said, how many ways can I assign these people to different positions? Okay, we could take this 792 and multiply it by how many different ways you can arrange a group of 5. Okay, which would be this times 5 factorial. You basically would get rid of that, and it would tell you how many different arrangements you can have. Center, point guard, all that stuff. Yep.
Can you get the 5, 4, 3 to the bottom?
The 5432 came from right there. 5 times 4 times 3 times 2.
Oh, and the 7 is
Went to
canceled out.
Larry. Oh,
Yeah.
yeah.
And the 7 canceled into the 12 factorial. Yep. Okay. Any other questions on that? All right, so that's counting. Okay, so our test on Friday will cover inductive proofs and counting. Tomorrow we'll have a review day to go over both of those topics. Okay, homework, it's on 631. Okay, 1 to 5, 7 to 12, 14 to 19, and 21 and 23.